I am Louise, and I'll be presenting my last results on the study of the dynamic model of excited laminar premixed inverted conical frames. First, this state of art. Why we decided to study this? Because combustion and thermoacoustics is the main problem in aircraft combustors. As we can see here, a combustion chamber of an aircraft that is damaged by this coupling of combustion and thermoacoustics. And the design of those engines relies heavily on CFD models, but performing such detailed simulations remains a challenge since there is a high burden linked to those simulations. Then my work here is devoted to develop and characterize those complex systems. My main focus is the combustion modeling and coupling with thermoacoustics, which are those unstable damaging behavior. This thermoacoustic stability is served from velocity disturbances that cause flame speed and burning area perturbations, causing also heat release oscillations inside of the machine, which also will come back leading to velocity disturbances. This problem is not only present in big systems like combustor, but also in simple systems like domestic boilers or laminar frames, such as the inverted conical frame. And as previously said, it relies on dozens of chemical species for the combustion side, leading to high computational burden. And I will be here showing, presenting the use of CFD and as perspective use of reduced data models to predict this flame behavior. So I'll be studying the inverted conical frame, also called as ICF, and its geometry and domain used for developing my model with Fluent. So what is this inverted conical frame? Is a laminar frame with premixed methane air fuel. It's a lean flame with equivalence ratio of 90%. And it's a frame that is anchored in a central cylindrical rod, as we can see on the right figure here. It's an axisymmetric frame. And why I choose this one? Because, however, even though it's a laminar frame, it is still prone to thermoacoustic instabilities. So here I'm presenting the domain and the characteristics of my model, which is based on experimental setup from Durox from 2005. As we can see here, it's my domain. There is an inlet of air, and on the center, the yellow arrow, sorry, the inlet of fuel, the mixed fuel. And in the middle, the bluff body. And in this region, marked in red, is where the flame will be anchored. So a first study was developed before the Fluent model, which is a simple 1D premixed flame developed at Shinking Pro. With the skeletokinetic chemical model, I am using for the CFD modeling, which is the DRM19. From this study, this simple modeling, we were able to obtain, as showed in the figure, but also a lot of other properties of linked to the DRM19, such as the mass fraction of CH2, OH, and the profile of temperature, as shown in this top right figure here. And then observing those graphics, we can see that the higher temperature achieved by the flame, also called as the adiabatic flame temperature, is 2200 Kelvin. When we look to the profile of CH2, which is the smallest space scale in those in the substance properties of this combustion model. We can also obtain the flame thickness since CH2 is linked is a substance that is produced and consumed inside of the flame front on the combustion region. And this flame thickness is 120 micrometers. And also from this model, we obtain that the minimum mesh necessary for obtaining a valid model is of 5 micrometers. So now about our specific model, fluent model. We are using a chemical kinetic model that solves volumetric reactions and use the Steve solver with ISAT table, and again with the DRM19 kinetic mechanism. And our fuel and their compositions are given in this table here. So to actually achieve the minimum mesh necessary size of 5 micrometers, we are actually using a tool from well-known tool from CFD, the mesh adaptation tool. Such that since our domain for the simulation is big when compared to the flame characteristic size, we can use a mesh base, characteristic mesh base of 100 micrometers. And with this adaptation tool, we can reduce the mesh size only on the regions where we are interested, so the region where the combustion happens. As we can see here, we are using a refinement gradient of 50 Kelvin per meter and a corresponding gradient of 250 Kelvin per meter. And on the image on the bottom, I'm showing first the characteristic mesh without any adaptation. On the second figure, I'm showing the same region, but already with the adaptation. And we can see that the adaptation is made only on this small region, which is linked again to the gradient, gradient of temperature, so the combustion region. And on the last figure, I'm just giving a zoom on this region so that we can see that the mesh is well refined and quite smaller than the mesh characteristic mesh that we set in the beginning. And one add information here is that the mesh we achieve in the end is slightly smaller than the necessary mesh of 5 micrometers. So it's around 3 or 4 micrometers. Then for my specific scenarios from the modeling I just presented, we are using a premixed full velocity inlet that is variable with time so that we can excite the flame willing to, after that, obtain some information to compute thermoacoustic and combustion coupling analysis. I'm using an harmonic function as shown here, where Vd is the mean RMS velocity constant that is also used on the experiment from the Hawks with a value of 2.05 meters per second at the outlet of the tube, of the inlet, fuel inlet tube, and an amplitude for the harmonic function of 0.14 meters per second. So as I said, I want to, in the future, characterize the flame transfer function. So I'm exciting the flame with several frequencies, varying from 75 Hertz to 250 Hertz. And I'll be presenting the results for this model, these scenarios in following. So the flame transfer function I'm using it here, as I said, to characterize the flame dynamics in relation to the instabilities we previously discussed. And it allows us to relate the flame response to incoming instability, incoming modulations, incoming velocity instabilities in terms of heat release rate, Q dot, sorry, it's missing here, and in function of the frequency. So here it's the equation for the FTF, and I'm using also one hypothesis that the flame surface area fluctuations rate is approximately equal to the heat release rate, and I'm computing this flame surface area with the modeling with Fluent. And then we'll be further looking to the gain of the FTF, which is the modulus of the flame transfer function. So how am I computing this flame surface area? I'm computing based on the modeling results for the mass fraction of CH2, which gives the closest and a fair approximation to the flame front and thickness, as we can see here on the right figure on the left side. Then to obtain a better performance and better profile representation of the field, the flame front, I'm doing a binarization over the field of CH2, which is shown here. The equations to achieve that is shown here, such that we will actually use the alpha variable, which is the already binarized field of CH2, to compute the flame surface area fluctuations. Okay, so here I'm just showing the results for several scenarios, and there are some remarks that I'll be talking here. First, we can see that there is a clearly different flame response for, sorry, oops. Okay, oh my. I am so sorry for that. But then again, we can see that there are two behaviors for the flame, basically for lower frequency response and high frequency response. So the lower frequency response are linked to the three top videos, where we can see that the flame is mainly flame base has mainly two shapes. One is the V, a narrow shape, as we can see here, and it they say changes its type of V shape to a wide open V shape from time to time. This is harmonic behavior. Meanwhile, the higher frequency forcing is mainly steady V shape due to these wrinkles that basically stabilize the flame. Then looking to the low frequency forcing, we can see that there are two main things happening on the flame. First is the wrinkle that is formed on the anchor point here on the base that develops on the flame front until it causes the pinch off on the flame on its tip, on the flame tip. This behavior is seen for the three frequencies shown here, low frequency shown here. I'm sorry, the video stopped. I don't know why. And a similar behavior is seen for the higher frequencies, where we have the wrinkle forming on the anchor point on the flame. It's possible to see it traveling along the flame front until it also achieves the flame tip and causes the pinch off of the flame. So to actually assure and see how this behavior is seen on the flame surface area fluctuation. I computed the flame fluctuation linked to each of those forcing frequencies as previously shown, and it underscores here those plots qualitatively that there is a switch between the forcing the response of the flame with the low frequency forcing and high frequency forcing. So we can see that for 75, 100, and 125 hertz, the flame has a harmonic visible response. Meanwhile, when we increase the forcing frequency, this behavior gets it's different. So to characterize that, the flame, the Fourier transform, fast Fourier transform, was developed for each of those signals. And it's here presented. And on the left side of each figure, I'm showing the FFT, sorry, of the surface area for each of the forcing, and on the right side, it's the FFT of the velocity of forcing. Just to compare the forcing frequency with the frequency response of the flame. Then I will split this explanation into three parts mainly. So first we look to the response of the flame into 75 and 100 hertz, where we can see that the flame mainly responds to the forcing frequency of in case, right? Such that the highest energy is linked to the same frequency that we are forcing, so 75 hertz and 100 hertz. However, when we come to 100 hertz, we start seeing some sort of harmonic here. Then in 300, that decreases and goes to zero. When we achieve the frequency, the forcing frequency of 125 hertz, the flame FFT amplitude decreases remarkably, as we can see here, when compared to the forcing amplitude. And this phenomena is actually due to the interference of two phenomena that I've just explained, which is the wrinkle and the pinch of the flame. Sadly, I was not able to show on the video because it's not running. But actually what happened is that the pinch off of the flame interferes with the frequency of the wrinkle. And this interference causes the flame to be slightly shorter in length when compared to the other ones. And that's mainly what I believe it's causing this effect on the FFT. Then when we go to higher frequency, the FFT amplitude switches to a broadband response, mainly concentrated on the low frequency region. In the forcing that we are inputting and forcing the system has not a big impact on the frame response. As we can see for 172 hertz, there is a small energy concentrated on the 172 point. And for the higher frequency, we don't even see any energy related to the forcing frequency. And this I believe it's mainly linked to the natural flame response, natural flame behavior. It has its own frequency behavior. Then after that, was able to compute the flame transfer function and the gain and phase linked to the flame response of our model. As you can see on the right side figure, it's presented the gain and phase linked to my model and in comparison to the experimental results from Duhoksen et al. From 2005. And there is a good agreement. However, when we are in close to 100 hertz, 75, 100 hertz, we have a higher gain when compared to experimental results. And this, after some analysis, we seen it's actually linked to the choice of gradient for the mesh adaptation, which will impact on this value. It can make it better or worse. And when we go to around 125 hertz, that we see the decrease of the gain. This is actually linked to the phenomena previously talked about, which is the interference of the wrinkle with the pinch off of the flame front, which decreases the flame length and impacts also on the gain of the flame. After that, we can see that the gain goes back to the expected experimental value and has a good agreement until the end. For the phase, the plot shows a good agreement. Also, no main remarkable difference is seen. One may note that for these computations, I use a band pass filter, and the response of the flame is here used only around the forcing frequency, with error of 10 hertz around the forcing frequency. Okay. So our conclusion is that mainly our flame, the inverted conical flame, has two different behaviors. One, when we are forcing with low frequencies around 100 hertz, and one when we force with higher frequency, such that the main natural behavior of the flame is seen on the flame behavior. We achieved a good representation of the inverted conical flame in comparison to experimental results. And however, our simulations have a high burden. It takes 2 or 3 weeks to compute using the gradient that I've explained in the beginning. So our perspective is to use the ROM, the Dyna ROM, to compute the reduced order model of the inverted conical flame with the show data, and compute the flame transfer function equation with the model obtained with the ROM. This work is in progress, also in collaboration with Nilam and Michael from GE. And the third point of our perspective is to apply the state observer method that Niels talked a little bit about to simplify our prediction, also a work in progress in the moment. Then these are just our already published papers that you can read if you are interested in this work. And that's it. Thank you very much. I'll be happy to answer any question.